The last concept we are going to talk about today is probability generating function. And this is very related to the generating functions we talked about in counting methods. But this is a special kind of generating function. And here, if you have a non-negative integer valued random variable x, so you have a random variable that takes values in, let's say, natural numbers, 0, 1, 2, 3, etc. In this case, the probabilities for each possible outcome, so the probability of 0, probability of 1, probability of 2, probability of 3, etc., it forms a sequence. And what we mean by a probability generating function is nothing but the generating function of this sequence. Okay, so the probability at k times z to the power k. Well, earlier we had defined the generating function in terms of x, but this is a function defined in terms of z. Apart from that, nothing is different. So the probability at 0 times z to the power 0 plus probability at 1 times z to the power 1, probability at 2 z to the power 3, etc. ad infinitum. Okay, so why is this called probability generating function? Well, as we have seen, because it is the generating function of the probability sequence. Not only that, but if you have the probability generating function given to you, you can actually retrieve the PMF from the generating function. If you just evaluate it at z equals 0, because these terms will all disappear, you'll just have this term, the probability at 0. And if you differentiate it just once, this term will disappear because it's a constant, and this z will disappear, and these will be terms with a z in them. So if you take it, the derivative of it once, and what you have is something like this, and evaluate it at, again, z equals 0, these terms will also disappear, and we are left with the probability at 1. Similarly, if you take a further derivative, the second derivative, so this is gone, this is also gone after the second derivative, and this will be just by itself, plus, well, you'll have the 2 here coming from this power, 2 times probability at 2, plus a function of z. Z is something times z, plus something times z squared, plus something times z to the power 4, etc. So again, if you evaluate it at z equals 0, you will get, this will disappear, and you will get this. So the probability at 2 is equal to 1 over 2 times the second moment of the generating function evaluated at 0. So you generalize this. If you evaluate the kth derivative of the generating function at 0 and divide by k factorial, what you get is the probability at k. So from the generating function, you can retrieve the PMF. But that's not the only property of generating functions. It's extremely useful when you compute the distributions of sums of independent random variables. I'm going to give an example at this point. Let's say x and y are independent random variables where you have these probabilities given to you. And we define z equals x plus y. Okay, we would like to find the PMF of z. Now, if you don't use generating functions, you can still solve this question. Of course, to find the PMF of z at k, we need to consider all outcomes of x and y when added up makes k. For instance, if you would like to obtain the PMF value of z at k equals 5, then the outcomes you need to consider are for x and y, 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, and 5, 0. Because if you have these two pairs, their sum will be equal to 5. So you need to compute the probabilities of all these pairs, compute them, and since they are independent, I'm multiplying their individual probabilities, and you get the result. And using this, you can compute each component of the PMF of z. So in general, you see this is a convolution operation. because here you have x at I, and y should be k minus I, and you add them all up for I from 0 to k. And this is essentially the convolution operation. And if you remember, convolution operation in the sequence domain becomes multiplication in generating function domain. So you can do this, but it's a little bit tedious by hand. So if you want to do this in an easier way, you use generating functions. And based on these distributions, you can write the generating functions of these two random variables in this way: 0.1 plus 0.2 z plus 0.1 z squared plus 0.1 z to 3, etc. And then the generating function of their sum equals the product of their generating functions. Okay, you multiply these. Of course, you don't do this by hand. Usually you use a computing tool, and this is the function that is the result. And when you look at this function, actually you directly see the probabilities here, because this corresponds to the probability that z equals 0, because it's the coefficient of the term z to the power z to the power 0. And this is z to the power 1, so this is the probability that z equals 1. This is the probability that z equals 2, probability z equals 3, probability z equals 4, and 5, as you see, 0.15, the same quantity we have found, and so on. For instance, this is the probability that z equals 10. Okay, so this is the way you solve such questions using generating functions. And this, by example, you see this is a simple example, and maybe the generating function may not look easier than the alternative. But if you have, let's say, the domain of each of the random variables is large, maybe you have an expression, or maybe you have lots of random variables to deal with. Maybe, for instance, z equals x1 plus x2 plus dot 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 x 48. If you have 48 random variables, z is the sum of them, and obtaining the convolution is very tedious in such cases. But if you write the generating functions and if you multiply them using a computer, by just looking at the coefficients, you can just retrieve the Pmf of Z. One final remark, be careful, this is only for independent random variables. You can apply this generating function method I explained here only when the random variables you add are independent. But in general, you see, this makes our life a lot easier as opposed to one by one taking the convolutions. And so you need to find a convolution between the two, and then the result, you need to find a convolution between this and this, another convolution. So you need to perform 47 convolutions, for instance. So using generating functions, you just perform one multiplication throughout, and by looking at the coefficients, you get the distribution right away.